Iterated. Whoa, what's that mean? Function.
Is there a repeated or recursive?
Yes, good. Systems. Okay, let me just get the door. Oh, this is the ghost door. There we go. Let's try that. So, we'll leave that as the heading. A little subheading is, there's another name for what we're going to have a look at today. They're also called dynamic sequences, and you'll see why shortly. Now, remind me again, what topic are we under?
Beauty and maths.
Beauty and maths, and specifically fractals most recently, right? And we spent all this time looking at, weird shapes that like this. How'd I do it? Something like that, and then like that, and you get the idea, right? Or triangles, or angles, and weird kinds of shapes. Very time-consuming sorts of shapes, okay? Now, we've been approaching fractals in a geometric way, which makes sense, right? Because what was our definition of a fractal? What is a fractal? There's
It displays like self-similarity.
Good, okay, so let's try and boil it down, because I gave you like a full long sentence thing, right? But it's kind of like a shape with a weird special kind of scale symmetry, right? I think that's the most important idea that we can boil down, right? You zoom in, you find the same kind of shape over and over again, right? And this kind of shape happens in real life, like rivers and galaxies and all that kind of thing. Now, we've been approaching it from a geometric point of view. That's what we've been doing, as I said. We were doing drawings, and I was like, bisect this, trisect that, etc. Today, we're going to approach the same fractal idea, but in a way that you very much wouldn't expect and doesn't look obvious at all, namely rather than geometric, an algebraic approach. Okay? Now, I just want you to keep this in the back of your mind, like this is kind of where you're headed, okay? Because for a long time, as we look at these kinds of things, whatever they are, it won't be obvious that we're thinking of fractals at all. Okay, so just keep that as the context. Right? I just need my piece of paper. Okay, now, let's look at this idea here. Try and unpack this. Probably the easiest idea in here that you know about is a function. What is a function? Can you give me an example of a function? Yeah, Nikita.
Substituting one value into the function.
Good. Okay, so a function is. Now, there's lots of different ways to say this. I'm going to take that as a starting point, right? There's kind of like an equation or an expression, right? Or if you like, even more generally speaking, a rule is a rule, right? That you put a value in and you get something out. Did you want to add something as well?
A function is when you put one, for every y value there is only one x.
Okay, so yeah, you're starting to get really specific. I'm going to try and keep it sort of verbal, right? So we said it's a rule or an equation or an expression that, now here's the important phrase, that maps one value to another. Maps one value to another, okay? And you know tons of these, right? So because they're all functions, we tend to denote them like this, f for function of x, right? So we're going to put a value into this, right? And then depending on what happens over here, you'll get some other value, right? So simple example, okay? X plus 1. Okay, this is a function. It takes one value and it'll map it to another. So we would write, for instance, f of 0. It maps to 1, right? So 0 and 1 are mapped to each other, okay? Or I could say any value I like. F of negative 100 is going to map to negative 99. Okay, so you're getting all these pairs, right? And you're seeing what's going on. So we know what a function is, right? But an iterated function says, now, don't just do this once. What was the idea of iteration? Do you remember what we wrote down a definition, didn't we? What was iterating about? Good, it's about this repeated process, and we thought about that geometrically, right? It's like, take something and then divide it up, and then divide what you've got up again, and so on, right? So we can apply this process not just geometrically, but algebraically, right? So, okay, here you go. Let's think about this. Let's come back to this guy. So if I treat this as not just a function, but an iterated function system, okay? We'll start with 0 again, because that tends to be the place where we start, right? And you get 1. But then you put it in again, right? So now I'm going to iterate, okay? And in this case, you get 2. So I'm getting these numbers, 1, 2. You can tell me what the next one will be. 3, 4. So this particular sequence that I get out, it's called a dynamic sequence because it's changing. This particular dynamic sequence that we get out of this iterated function system, we give these a name. This sequence. This is the sequence of all counting numbers, or natural numbers, if you like. Okay? Now, it's a pretty boring kind of sequence, okay? So let's have a look at some more interesting ones. I'll leave that one there for a second. Let's have a look at, now, do I want plus or minus? Where did I write it? I think I wanted plus, yes. Let's have a look at this guy. Now, you might think, well, is that really all that much more interesting than the previous one? And I'm going to suggest that it will be, yeah. Can you what?
Isn't it odd numbers?
Well, let's have a look, shall we? Now, remember, this idea of a function is you put values in and then you get values out. And iterating means do it over and over again. Okay, so again, we'll start at 0. We're pretty much always going to start at 0. Okay, so f of 0, what are you going to get? Okay, 1, so you're like, great, starts off pretty boring, okay? Now I take this value and I iterate again. So you go f of 1, okay? So now when I put 1 in here, I'm going to get 2 times 1 plus 1, which is 3. Okay, odd numbers so far, right? Iterate again. Okay, so now I'm going to go f of 3. Okay, so it's 2 times 3 plus 1. Still an odd number, but I've missed one, haven't I?
5.
Let's go again. Iterate again, so f of 7, right, is going to be 2 times 7, 14, plus 1 is 15. Okay, can you keep going? Tell me what to do next. 1, 3, 7, 15. Hi, Mr. Johnson.
Hey, they all working hard, Mr. Wood?
Oh, absolutely. They're really,
Are they?
can't you tell?
I hope so. They look engaged. What year have we got? Year?
This is stage 5, year 9 and 10.
Year 9 and 10. Fantastic. So what are you working on?
Fractal, sir.
Right.
Well, we're getting there. We're not quite there yet, but we
Getting
will
close.
get there.
Getting
yes.
I got held up. My apologies. So
That's
they
no
just
problem.
gobbled up all that time. So
That's right. Well, I'll be here until end of 6, so
Yeah.
might catch you next week if that's
yeah,
okay.
it might have to be the best.
Thank you.
Cheers. Bye bye.
Being called by the principal? How's that rate on? Anyway.
Oh, he didn't actually come on the screen.
Yeah, oh, we got the sound of his voice.
First time you mentioned people being a customer, someone
There you go, see? It's
Interruption
Yeah,
number one.
Murphy's Law. Alright, sorry. Where were we? Now I'm going to stop writing all of these because you can see I'm just going to start to write the sequence out, okay? So we've got 1, 3, 7, 15. What's next? You double, you add 1. Okay, double, you add 1. Are you starting to recognize what these numbers are? The next one's going to be 127.
That is good.
I don't get it.
The next one's going to be 255, 511, 1,023. Are people recognizing them yet? Now, have a look. Now, this is interesting. We kind of predicted, and it wasn't a bad prediction. We predicted that this would give us odd numbers. And it has given us odd numbers. But it hasn't given us the odd numbers. Why not? It's because if I just took successive values of x, if I did f1, f2, f3, f4, f5, and so on, that would give me the odd numbers, which is great. But I haven't done that, have I? I have iterated. Right? So we're trying to wrap our head around this process, right? Which is eventually going to lead us somewhere like this, mysteriously. Okay? Algebra, geometry, just two halves of the same coin. Okay, two sides. So what are these numbers? What are these numbers? They are always 1 less than a power of 2. I was a bit naughty. I left off 0, right? So if you add 1 to all of these numbers, you'll get 1, 2, 4, 8, 16, 32, 64, 128, all the powers of 2. Okay? So if you like, you could say it kind of like this. Here's a way that mathematicians do this. Let's say the nth term, right? Term n, okay? It's kind of equal to a power of 2 minus 1. Right? And this is an important sequence, just like this one's an important sequence, but this is a bit more boring. Okay? This sequence that we've just generated here is called the Mersenne sequence. Unsurprisingly, named after a guy named Mersenne. Okay? Now, Yeah, question.
So the sequence that you just read above is called Mersenne sequence.
This one here.
Yeah,
one.
that's called
Yeah.
Mersenne.
That's right. Okay. Now, some important things to note here. This Mersenne guy, he did a lot of important things, particularly to do with prime numbers. In fact, some of these, not all of them, some of these are prime. Can you see some of them are prime, but not all? Which one's a prime? 0 prime?
Yeah.
0 is kind of weird. He stands in a corner. It doesn't have anything to do with everyone else. He's in a class of his own. 1 prime.
Yeah.
No.
No.
One can't be prime. One can't be prime, right? I can. If you. By the way, later on we have a double, so we'll see how we go. I don't know how many of you learnt 1 isn't prime because. And then what was the reason that got supplied to you? There's a very important logical reason, and it's bigger than the 2 factors thing, even though it's a good reason. There's a very important logical reason why 1 can't be prime. If 1 was prime, it would break the universe. Okay, I'll let you think about it.
I want to hear about it.
All right, 3
Yes.
prime 7
Yes.
prime 15 no 31
Yes.
prime 63 no 127
Yes.
No, it's
This is not.
This is
1 plus 2 plus 7 gives me 10, so not, it does look, I think it is prime. 255, clearly not prime, okay? I don't know what starts to happen after that, okay? But here's the important thing, right? These primes in here, and there are lots more after this, they're called Mersenne primes. Okay, now we're gonna spend a lot of time looking at those later on, but I just thought I'd mention it since here's the sequence. Okay, so now you're introduced to this idea of an iterated function system. Okay, the idea of taking a function and then going over and over again and repeating it. Okay, but these two are pretty pedestrian. They're pretty simple. Okay, so I'm going to give you a bit of a harder one. Just give me a second while how much can I rub off? Rub off everything except for the title.